Hello, my name is Nathaniel Jose, and today I will be discussing my Physics 2211 Lab 2 Motion of a Falling Object. So, to introduce this lab, the purpose was to measure an object's motion from a state of rest at an elevation to its impact with the surface, as well as compare the experimental data collected to two different computational models, one with just gravitational forces and one that calculates the effect of drag on the object. And a brief results of this lab were that the graph with gravitational force and drag force was more accurate than the computational model that just calculated gravitational forces. The fundamental principles that we're exploring in this lab are Newton's second law, which states that the rate of change of momentum on an object is directly proportional to the force applied on that object, or F equals mass times acceleration. We will also be exploring gravitational forces, the formula being force of gravity equals negative mass times force of gravity times j hat. And as you can see in the diagram here, where mass times gravity is equal to gravitational force. We'll also be exploring drag force. The equation drag force equals the proportionality constant times the objective's velocity squared times the velocity direction. And the net force is just force of gravity plus force of drag, which is the entire system. For the setup, the experiment, the object in use was an expo marker, and the system was the expo marker, the gravitational forces, and the drag forces applied to that expo marker. The initial conditions, the start position is 0 meters, the initial velocity is 0 meters per second, and GlowScript is used for the computational trial. Here is the video of my tracker. As you can see here, the expo marker is dropped from said initial position, and you can watch as the Y position slowly makes this downward sloping curve. Here are the calculations for the first computational model without drag. As you can see, the constant is 0 in this calculation, and the force of gravity, the gravity constant, is 9.8. For delta t, it's 0.03, or circa 1 over 60 frames per second. And then, as you can see here, we're doing the standard equations for ball velocity and ball position, where F net divided by ball mass times the change in time. And for ball position, it is ball position plus the velocity of the ball times change in time. Here is the data collected from the tracker versus the simulation. As you can see in the simulation, since it is not calculating drag, it in fact ends at a lower distance than the tracker, which has drag in it. And then for the second computational model with drag, now our constant is 3, and our calculation for the net force changes to account for drag force here, where the magnitude of the velocity squared times negative j hat is equal to force of drag. And as you can see here, the Y with drag now closely aligns itself with the Y tracker, which should happen, and the Y simulation is still an overestimate of what the actual experimental data produced. So now the discussion. Which models, if any, predict the terminal velocity? None of these models would predict the terminal velocity over the short amount of time in which the object was tracked. If the object were allotted a longer time to accelerate to the point where the force of drag equals the force of gravity, then a terminal velocity would be achieved and the net force would equal 0. So, what if the ball was initially thrown downward? If the object were thrown downward instead of dropped, the terminal velocity would not change. It would just achieve terminal velocity faster. In a model, the initial velocity of a thrown ball would be greater than is the object where it was just dropped from a state of rest. The object would accelerate until it reached its terminal velocity, where the drag force, of course, is equal to the gravitational force acting on the object. So some of the errors that I predicted would be in this lab are imperfect precisions from the human aspects on the applied force, wrong calculations or inputs, and of course the angle of the video that I put into tracker. For the computational model, it could be programming errors or incorrect inputs on my part.